All right, lesson number 4 is all about hypergeometric distributions.
It sounds more exciting than geometric distributions.
It does.
Yeah.
It does. It
yeah.
sounds more energetic.
More energetic.
Perhaps
Holy smokes.
a little bit harder to understand.
Yeah.
But really, hypergeometric is just the name of it, okay? And it's not. It's actually completely different than a geometric distribution.
We've been looking at geometric and binomial and even uniform where all of the probabilities are independent.
Yeah.
Right? Where you have all these independent outcomes. But hypergeometric, if you had to make a Venn diagram, it's completely separate from geometric and binomial in that these are dependent, which means we're not replacing the card after we draw it out.
We're not replacing the marble once we've taken it.
We're not replacing the person once we've put them on the committee. Right?
Yeah.
What's good about hypergeometric distributions is that it's just going to take advantage of what you already know about combinations, about what you already know about splitting things into two piles. This pile of things we want and this pile maybe of things we don't want, and then just finding combinations. Okay, so there's going to be a lot familiar about hypergeometric distributions, and when you're reading a question on a test and you're trying to figure out, holy smokes, is this uniform, binomial, geometric, or hypergeometric? If it's a question where they're dependent probabilities, where we're taking something out and not replacing it is what's happening, then straight away it's hypergeometric. That's how it differs from all the others.
All right, so a couple examples of where we're going to see this. When choosing a starting lineup for a game, a coach just must choose a different player for each position, right? That would really be dependent on who I choose first and put them in this position, or who I choose second and then I put them in this position. So the probabilities would change, right? When you deal a deck of cards from a standard deck, there's no repetition, right? Like when you're dealing things out, there's no repetition of cards.
Once that card goes out and it's not coming back in the deck, so your probability of getting a card depends on what card has already been put out.
Basically, when choosing members to form a committee, there can also be no repetition, right? So all of these things kind of indicate something a little bit different. We're not replacing variables, and we have to use individuals in different ways. So here it is. The probability of X successes in R dependent trials is given here. The probability of X is equal to A choose X times N minus A choose R minus X, all divided by N choose R.
Okay.
So, where A is the number of successful outcomes among a total of N possible outcomes, holy cow.
This just seems like a lot of noise.
That looks so confusing. Yeah, there's lots of background noise going on here.
Here's the thing. What you need to understand is think about it like we were doing our combinations for a deck of cards. Say you want the probability that in your hand you'll have 2 queens, right? We are going to make 2 piles. If we're counting queens, then
There's
the
4.
A value is 4, right? And so we're going to have 4 choose 2 as our A choose X up there, right? If it's going to be a 5-hand card, then we know that the denominator is the no restrictions value, the 52 choose 5, right? So if we've already got a pile of 4 queens off to the side and we're choosing 2 of them, and we know that our no restrictions is 52 choose 5, that's N choose R, then that means the rest of the pile that's not queens is 48, so that's your N minus A, and then the rest of the hand that's not queens is 5 minus 2 is 3. So again, this is following the same rule where the A and the N minus A, those 2 upper values, will add to N, that's in your denominator, and then the 2 lower values in your combinations, your N choose R's in the numerators, will add to the R value in your denominator. So again, it's just like we're separating it out into 2 piles. It's just that if we're counting queens, then queens are what we're concerned with. So A is the total number of queens, and then how many we want is X. So, that 4 choose 2. So all you need to consider is whatever it is that you're counting, whatever it is that you're concerned with and you're wondering how many and what's the probability of this many, put that first in your numerator. And then create a product with the rest of the pile and the rest of what's in your hand kind of thing.
All right.
Okay.
It's going to help you when you see this example because this is very, very common. We've done this. A committee of 5 is to be chosen from 6 men and 8 women. You've seen this before, right? We're choosing a committee of 5. But now instead of the second sentence of this problem saying, find the probability that 2 out of the
5 are
5 are men, or that 2, like now we're not finding just 2 out of the 5.
We want
we're finding
the distribution.
the whole distribution for the number of women.
Yeah.
So we could have 0 women, we could have 1 woman, 2 women, 3 women, 4 women, or all 5
women. Yeah.
So that's the distribution that we're looking for. So we're not just, the second sentence of this isn't to find the probability of X number of women.
Yeah.
It's to find the probability of basically
all the
different possible outcomes.
Yeah.
Okay. So the number of women on the committee, first of all, if we add up 6 men and 8 women, we're talking about 14 people.
14 people.
Okay. It's a committee of 5, so it's going to be 14 choose 5.
So no restrictions. This is your denominator.
Yeah.
N choose R is just going to be 14 choose 5.
Okay.
Okay.
We're talking about a distribution for the number of women. So because we're talking about women, because that's what this problem is about, A then becomes about the women, right?
Yep.
And then, of course, our X value could be 0 women on the committee, 1 woman on the committee, 2, 3, 4, or 5.
Notice we don't do 6, 7, or 8.
Because then the committee would be too big.
The committee is only 5. Yeah. So we can go from 0 to R. You know, we don't go from 0 to A on this necessarily.
Yeah.
Sometimes you will, but there you go.
Yeah.
Okay.
All right. So the probability then of each of these would be the probability of no women on the committee would be your 8 choose 0.
Right. So here's a pile of 8 women. We want none of them.
That means that out of the 6 men, we're going to choose 5 of them because they have to form the committee.
Yeah.
So 6 choose 5.
Yeah. And
we divide by the no restrictions case, which is 14 choose 5.
And notice that in terms of N and R, in the numerator, the 8 and the 6, those two sort of N values, the two upper values for the combinations, would add to your 14. And then the 0 and the 5, the two lower values for your combinations, should add to the 5. Okay, so then we're just splitting those 14 people into 2 piles. And now we're saying, what's the probability of 1 woman? Well, there she is.
So it'd be 8 choose 1.
Yep.
And then out of the 6 men, we're choosing 4.
Only 4, because we have to drop down.
Okay.
So we can only have 5 people on this.
In the next case, 2 women, 8 choose 2. And then, of course, out of the men, we choose 3.
Yeah.
And so on and so forth until we get to our whole entire distribution.
Sure.
Right? And we know that the probability, if you got 14 people and 8 of them are women, the probability that you would choose randomly a committee of no women would be a small probability.
Yeah, because there are more women than men. And each of these probabilities, I mean, this should sum to 1.
Yeah.
Okay, so when you're doing a distribution, if you want to check your work and make sure you're doing all your calculations right at this point, you could do 6 plus 120 plus 560 plus 840 plus 420 plus 56 equals, and it'll get you 2002. And then you know that those probabilities all add to 1. So we've done part A, which is determine a probability distribution for the number of women on this committee.
There it is.
There it is. There's all the possible outcomes from 0 women all the way up to 5 women on this committee of 5. And then part B is, well, what's the expected number of women? Like if you were to do this
totally
forever
random,
average it out, you know, like how many women would you expect to find on a committee of 5 under these circumstances? So we're going to do 0 times 6 over 2002, and then 1 times 120 over 2002, and then 2 times 5, 6, and so on and so on. And notice again, you could be reducing these, but we chose not to reduce the probabilities because now they're easier to use, and it's easier to add them up. And especially for these types of distributions, we do not recommend that you change these into decimals or round them because you want this to be precise. You want these probabilities to add to exactly 1. And so keep the fractions here. Don't change them.
Yeah. Good advice.
Yeah.
And so when you add this up, you get 5,720 out of 2002.
Okay.
Now
you can divide
we can go to it. We can go to a decimal. And this is about 2.86. So what does this mean? 2.86 women. So if out of 8 women and 6 men, we're looking at a committee of 5. Basically, the expected number of women, the ones that we would see on average if we were completely choosing from random, we would expect to see either 2 or 3 women, but probably closer to 3 women.
Definitely more than half. Because out of a committee of 5, 2.5 is half.
Yes.
So more than half of the people on the committee should be women. And that makes sense because there were 8 women and 6 men to choose from this committee. So it was more likely anyway.
All right. So expected values, however, and this is another workaround, right? So if you can't do, or if you're not going to do the full distribution, here we actually have a way of calculating expected value, right, for a hypergeometric.
Yeah.
And the expected value in this case is R times A divided by N.
Okay, and so one way to interpret this is, if you're talking about women on your committee, you know, then we had A of them, so we had 8 of them. And the N value was the total number of people, which was 14. So essentially that A over N part is just 8 over 14. It's just the proportion of women out of the total group.
Yeah, so this is totally a proportionality.
This is totally proportionality. So then if you've got the women over the total, which is A over N, but you want to repeat that 5 times, because you want 5 people on your committee, then when you do 5 times 8 all over 14, that's going to give you the expected value in terms of your proportions, right?
So let's see how that works.
Okay.
A box contains 7 yellow, 3 green, 5 purple, and 6 red candies. They're all jumbled together.
Okay.
What's the expected number of red candies among 5 poured from the box? So you've got all these candies there in a box. If I randomly pick out 5 candies, how many red could I expect?
All right, well, that's 5 candies, so we know that R, which is, you know, what's going to be in your hand, is 5. I got to figure out N, like, you know, how many do we have to choose from in the first place?
Well, we could say that N is basically equal to the total number of candies. So we get 7 plus 3 plus 5 plus 6. So we get 21 candies all jumbled together.
Okay.
Okay?
Yeah.
We're pouring out 5 of them.
Okay, so we know the R is 5.
Yeah.
We know the N is 21. If I want to just find the expected number of red.
Yep, so how many red candies do I have?
Is how many red.
Yeah, because if we're interested in red, A is what we're interested in.
Yep.
So A is equal to 6.
Okay, so I've got R, I've got A, I've got N. I want E of X. Like I want the expected value for the discrete random variable. Okay, so we'll just substitute into our formula.
And so basically we get 5 times 6 divided by 21. So I would expect that in this mix of candies, if I pour out 5 or if I pick out 5, I would expect 1.43 candies. So
to be red.
To be 1 or 2 red candies.
Yeah.
Right. Basically, though, again, this comes back to this idea of basically a proportion. Is that, okay, well, here's what I poured out.
So R is what's in your hand.
Yeah. Here's what's in the box.
N is what's in the box.
Right. So if I've got 6 out of 21 in the box.
Yep.
Right. Then I would expect the number that I pour out
to be proportional.
To what's in the box.
Yeah.
And so this might be, for some people, an easier way of expressing this formula is to basically think about it like a proportion.
Yeah.
That, hey, if I've got 6 over 21 in the box, then what I pour out had better be in proportion to that. And
because
of course
it's a sample. So I would say, write this, like go back up to that little box where we've got the formula in there, and write this in. Because there are going to be some times where you are solving for A.
Yeah.
And you're not finding the expected value. They're going to tell you the expected value, and then you have to find A or N or R or some other value. But really, it's just a proportion. However many you have in the total, if you're taking a sample, it should be proportional out of what's in your hand. Yeah.
Here's the proportion explicitly written out.
Yeah.
Okay. All right, so in the spring, 500 dinosaurs were caught in a wilderness area.
Okay.
The dinosaurs were released after being outfitted with laser vision.
Good. It's important that they have that in the wild.
Yes, exactly.
Yeah.
To estimate the dinosaur population in the area, rangers caught 40 dinosaurs in the summer. Of them, 15 had laser vision.
Okay. Estimate the total population.
So basically what we're being asked to find the total population. So we caught 500. We gave them laser vision.
Yep.
So 500 out of the total population, whatever that is.
We don't know. Yep.
500 had laser vision.
Yep.
So then we release them.
They intersperse and intermingle with the population.
They mingle, everything becomes random,
yep.
And then we select a sample of 40.
Yep.
And we look and we see, oh, well, 15 of them had laser vision, 15 out of 40. So we would expect that if 15 out of the 40 had laser vision, that would be in proportion with the 500 that we gave laser vision to over the
total number of dinosaurs in the population. Okay.
So we're looking for N.
Yeah. It's like the total number of candies in the box, people.
Yeah.
Yep.
A is equal to 500.
Because that's how many dinosaurs
have it.
Just like how many red candies were in the box.
Total number with lasers. R is equal to 40 because that's the number that we caught. That's the number of our
hand.
sample.
Yeah, that's what we've got in our sample. Yep.
The expected value is 15 because of the range of the dinosaurs that were in our sample, 15 of them had laser vision.
Laser vision.
And so we can set up our proportion. We can say, well, the population is 500 times 40 divided by 15.
Yeah, so we're just going to cross multiply. So you would probably write your next line. We haven't written in every single step, but you would probably do this proportional reasoning where you'd say 15 times n equals 40 times 500, and then divide both sides by 15 to isolate n, right? So we've just got n equals 500 times 40 over 15. So we can estimate that the dinosaur population is around 1,333 dinosaurs. Based on the fact that 500 had laser vision and the proportion of the ones we caught, was 15 out of 40. Okay, you will definitely see a question like this on your unit test.
100%.
Just put a star next to it and just expect it. That's why this proportional reasoning bit is so critical.